No.
Camera's on.
George Light.
All right, let's pick up sort of where we left off yesterday. We're going to back up just a little bit, kind of talk through it again. All right, so we were discussing ionization energy, which is the energy required to remove an electron from an atom, right? Okay. So the more, jot this little phrase down, in case we're not exactly comprehending this. The more difficult it is to remove the electron, the higher the energy. Okay. So it's an energy requirement. Okay. Yeah, the harder it is to remove the electron, the more energy is required. Or another way to say it is the higher the number, the harder to remove. So if you look at this table up here again, this table of numbers, this is the third period of the periodic table, correct?
Yes.
I see that on their periodic table. Have your periodic table in front of you because you got to be able to relate all this to that table. It's going to help it sort of lock into your brain, hopefully. So this is the third period, okay? Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, fluorine, argon, okay? All right. The trend says that as you go across that period, which is down the column in this table, as you go across that period, it gets harder to remove an electron, or you could say as you go across that period, the ionization energies get higher, right? So there's a higher energy requirement to remove an electron as you go across the period because of the greater effective nuclear charge. Okay? So we see here as a general trend that to be true. Okay? 495 and we end up at 1527, right? So these numbers are getting higher, generally higher, which means it's generally getting more difficult to remove the outermost electron as we go each element across the third period. But if we look, there's some exceptions to the trend. From here to here, magnesium to aluminum, it drops. So it goes up, down, down, from phosphorus to sulfur, then up. Okay? So there's two places where there's an exception to the trend. Look over here on the left now. The first place that we have the exception, okay, is between magnesium and aluminum on this period. If you look at the second period, that would be beryllium and boron, right? Same exception applies, just bump it up an energy level here. So what we're talking about is how to this electron right here, the one I drew in a different color, the orange electron, and this orange electron. It takes 735 kilojoules to remove a mole of these 3s2 electrons from a mole of magnesium atoms. Okay? So if I had a mole of magnesium, it would be a mole of those electrons. It would take 735 kilojoules of energy to take all those out of those atoms. According to the trend, it should be more difficult to remove this one from aluminum, so this number should be higher, right? But it's not, okay? It's been measured an infinite number of times by thousands of scientists, and it's not, okay? So, the question is, why, right?
It's because we block electrons don't penetrate.
All right, so, yeah, so, well, it's not further from, it can't get as close to, okay? So that's two different things, right? Okay? So it's not that it's further away, it's that it can't get as close as. Okay? All right. Reason being, this one's in a P, This one's in an S. As we saw on the little models yesterday, which I already put that back on the shelf. You saw in the models yesterday, the S orbital is a solid spherical region of density, okay, which includes the nucleus of the atom. So the electron can be as close to the nucleus and including inside the nucleus if it's in an S orbital. If it's in a P orbital, the nucleus is off limits. That's what we call it in quantum mechanical terms. That's called a node. It's a place where there's a zero probability. Okay, so that means that this P electron can never be, does not have the potential to get as close to the aluminum's nucleus as this S electron does to magnesium's nucleus. Okay, that's going to mean that in general it's easier to remove instead of more difficult, even though this is 13 protons versus 12. Okay. The second exception is a little easier to understand. Doesn't require quite as much visualization of probability regions as the other one did. So here we're comparing this electron. This is the outermost electron of phosphorus, and this is the outermost electron of sulfur. It's 1,060 kilojoules to get rid of a mole of these electrons, but only 1,005 to get rid of a mole of these electrons. According to the trend, this number should be greater than 1,060, but it's not. Okay. The reason why, even though this one is being pulled harder, because this is what, 16 protons versus 15, it's also being pushed by its partner right there. Okay, where this electron has an orbital all to itself. So nobody's trying to kick it out. Here, these two are pushing and shoving on each other all the time. That negates a good bit of that attraction to the nucleus. Even though it's 1 repulsion versus 16 attractions, these two are much closer together. So if we think back to what we said about Coulomb's law yesterday, I'm going to add one little extra thing to that. So Coulomb's law said that attraction and repulsion is based on the magnitude of the charge. Okay, so in other words, 16 pulls harder than 15. Okay, and the distance. Distance is more important than magnitude. Not going to deal with it right now, but if we look at the mathematical equation, the distance is a squared term. So distance is more important than the magnitude. So this one is being pushed by one charge that it's very close to, which makes a significant difference, even though it's being pulled by 16 that it's not that close to. Yeah.
You said magnitude of what?
Charge.
Question.
Uh-huh.
So, even though sulfur is 16 and phosphorus is 15, since the distance of those two are closer and they already don't like each other, it's easier for that one to leave.
Yeah, it's being pushed a little bit.
Okay.
This one up here is not being pushed very much.
And since there's nothing against it that's in a closer distance, that's why sulfur would be.
Well, it just doesn't have anybody repelling it. This one does it. This one does. Go ahead, Ms. Grant. You got to have a question about this. Of all things.
Look.
If you don't have a question about this.
Look. Okay. So basically, so are we saying that the P, like, are we talking about removing where it comes?
Remove. So we got no definition of ionization, right?
So the
Taking
P
the
would be
electron
harder
out.
to remove, yes.
It's much harder to remove than this one is.
Than that one because of the repulsion.
Right. But the trend says this one should be, but it's not.
Okay.
These are violations of the trend.
Okay, so in groups 2 to 13, it's based off of the
Or
level.
comparing 2 to 13.
Yeah, like when we did it right there, that's comparing the levels because S and
That's
P.
got to do with P versus S.
Okay.
This has to do with a half-filled P versus a full-filled P.
So that's good. 15 through 16.
That's 15 and 6, comparing 15 and 16. Well, yes, it goes back to 1255. Because now, that's not a single propulsion going on. It's the next one, and now we're up to 17 protons at that point. The proton trend takes over.
And on the exam, we'll have to explain why, but this will be an example of why.
So people can do your turn.
Yes.
All right, we're good with that now? This is that part of chemistry where you got to try to visualize something that can't be seen, okay? That's difficult. That requires using some part of your brain that we don't use on a regular basis, okay? So we got to visualize things that can't be seen.
That's all I do in this class, like, that's why I just visualize everything we say, and it makes it easy.
Yep. All right, everybody good with that? Okay.
This one is already repelling this one.
So,
It's already.
these numbers, the coaches, are we gonna do something with those?
Uh-huh.
Because it's already trying to get rid
Next
of
thing.
That's already.
Okay, so I know we just learned this letter.
Get my hand
But
ready.
was this B on the quiz tomorrow?
Did we say that yesterday?
Because there's
It's-
two
it
more.
won't.
You said either.
You said electron configuration.
We said yesterday that the quiz was on everything up to yesterday,
What?
Not
but not yesterday.
You said empirical formula and electron.
Yeah, which was not taught yesterday.
But that's,
taught
you
last
said
week.
everything up to today, there was more. Was there more?
So yesterday is not on tomorrow's quiz. That's what we said yesterday.
But everything else taught up to today.
Everything up until yesterday.
But it's more than just empirical. Empirical's not gonna
Yes,
add.
but that's what we're gonna do.
God, I forgot what I was gonna ask.
You should have just said like configuration and formula. You freaking us out with the.
I'm trying to answer her questions.
Mr. Cato, I feel like for me, I just gotta just draw it for you to understand it, because I can't say it. I like my questions, like I can't write them correctly. It's hard. It's so hard.
Well, I'm keeping up. Yes,
So can we like know what's gonna be on the quiz for?
something about empirical formulas and something about electron configurations.
Are you gonna do decomposition with empirical formulas or just combustion? Cause like when you were talking about that example that you showed me, like I wonder if you're gonna have something like that on there.
I don't think so, but I think this would be a really great bonus question. It's on page 131, 85.
Types the questions.
Like, we need you to read that. We need
Yeah,
you to
for real.
do an example of this for real. Do an example of that for real, cause you actually didn't know.
Maybe in a minute if I get time.
And I'm just saying, you know, Mr. Cato, I'm saying, I'll be like a really good bonus question.
Got it on.
Real. Yeah.
So question over here was, would it help to watch Khan Academy? Absolutely. Khan Academy, and it's linked on the front page of the slide, has the entire AP Chemistry course, okay? Like they've got a lesson for just about they've got a lesson on there for every major topic. Okay, so I know there's one about empirical formulas. Surely there's one about electron configurations. I don't know if there's one about these exceptions or not, probably. I'm sure there's one about periodic trends in general. I don't know if they get into these exceptions, but probably do.
They supposed to have like a little quizzes that you can do there.
They have quizzes, yep,
I think
an excellent resource. Okay, so what we've been talking about here with ionization energy is technically known as the first ionization energy. So how much energy is required to take off the outermost electron? So the electrons come out in the opposite that you would put them in. So if you're drawing an orbital diagram, you put them in a certain order, you take them out in the opposite order. Okay, so you take the first one off, it requires certain, let's just take magnesium as an example. It takes 735 kilojoules to take this electron away. It takes 1445 to take the next one away. Okay. For aluminum, we got 1, 2, 3 valence electrons. It takes 580, then 1850, then 2740. Okay. So it gets more difficult to remove an electron every time you take one away. So if I take one off, the next one's going to be harder to remove. And the next one will be even harder than that, and the next one, and so on. Okay? Now, notice though that there is a point. They've drawn a little line here for us to point that out. The AP exam won't draw the line. But notice that this jumps up by a factor of about 10, right? This is jumping by a factor of about 6, about 5, about 4. I mean, it's jumping by multiples, right? So it, for example, if you came down here to sulfur, it goes up, 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 and way up, right? If you follow across there, you'll notice that every one of them does that. Silicon goes up, 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 way up. Okay? The only one that doesn't do it, okay, is this, was it go to 7? Well, never mind, it doesn't go all the way to 8. Anyway, never mind. So there's a jump that takes place, a big jump, okay? That big jump happens when you try to remove a core electron. So for magnesium, has how many valence electrons? 2. So it goes up, up, and when you take the third one away, it jumps way up, right? Because now you drop down an energy level. When you drop down an energy level, it gets way more difficult to remove that electron. Aluminum has 3 valence electrons, so up, 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 and then the fourth one is way up. So silicon's got 4, so it goes up, 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 and then when you try to take the 5th one, the number jumps way up. Everybody follow that? Okay, here's a question they like to ask. Take something like this chart, cover that up, okay, cover up the symbols, all right? And they would tell you something like, these numbers come from the elements of the 3rd period of the table. Which of the following is, they might circle one of them or something, you know, be like, they circled this one, okay, and they say, which element could that be, right? So they're telling you the row of the table, give you that information. So you're going to go, well, and then I'm going to have this little dash, this little stair-step line thing. So you just go across there and see, where's the big jump? It's right there. So between the 4th and 5th electron, there's a huge increase in ionization energy. Happens between number 4 and number 5. That means that this element has 4 valence electrons. Okay? So you look at the periodic table, find the one that's got 4 valence electrons on that particular row. Okay? Or on multiple choice, they won't even tell you the row. They just give you 4 elements, and you just, one of them's going to have 4 valence electrons, the rest of them don't. Okay? Follow that?
Can you say the question again?
What question?
You said
How they'll ask it, which
Yeah,
one?
They ask it a lot of different ways. What you have to be able to do is look at that information and determine how many valence electrons something has. I don't know what the question is going to be.
Determine valence electrons based on.
Looking at those numbers, you should be able to determine how many valence electrons an element has. You look for the big jump in numbers. If it's between 5 and 6, then it has 5 valence electrons. If it's between 7 and 8, it's got 7. Between 1 and 2, it's got 1.
What's the answer to that?
That's how we know it's whenever it has that big.
The one I picked there has 4, so that would be silicon.
Okay,
Yeah.
so
So the valence electrons are the easier ones because they're already in the highest energy.
Which one is it again?
So
The 4th row, the 4th one, the 3rd period on the table, element with 4 valence electrons is silicon, right?
yeah. So
All right, so we have discussed atomic radius and ionization energy. Which one should we do next? Let's do ionic radius. How about that? Okay. Let's do this. I tell you what, before we go to that, let's back up to atomic radius. Talk about one other little scenario that. Everybody good with what I got? I can erase this.
I have a question. Which one did you pick again?
The fourth one.
Okay. I was counting all of them, so like I was it's so much fun when you like pretend.
Like based on being hot or based on, okay.
All right.
So you said that we-
There's four orbital, no, three orbital diagrams. All done? All right, thank you. Yeah. Breathe in. I agree. All right, so there's three atoms, electron configurations on the board right there, right? Okay, all right, two ions and one neutral atom, correct? Okay. They have different numbers of protons, right? 17, 18, and 19, respectively, okay? How many electrons does each one of them have? They each have 18, correct?
Yeah.
So chlorine gained one, argon stayed the same, potassium lost one. So they all have 18 electrons. Okay? So those are three atoms that have the same electron configurations. Three different elements with the same electron configuration. That's called being isoelectronic. Now write that word down. Isoelectronic. It's all one word.
Isoelectronic is when you say they have the
Three
same.
different elements with the same electron configuration.
Does it have to be 3 different elements or?
To any just yeah, it doesn't have to be three. Just same different elements with the same configuration. Okay. Now, question is, which one of those is largest? Or would they be the same size?
It would be potassium, right?
Potassium is largest?
Yeah.
Why?
Increasing energy levels.
I don't see a 4S up there.
Increases orbital size.
Do what now?
Increasing energy levels, like it increases the orbital size.
Because it lost the valence electron and gained one, so that one.
It lost and gained
No,
one?
no, it can't lose and gain.
I don't see a-
Like potassium is in the 4s orbital, which is larger than 3s orbital.
I don't see 4S up there.
Give us a minute, let us think.
Would it be CL?
Let's give everybody just a minute to ponder this. So we're looking for which one is the largest. of those three examples right there.
Oh, can I?
Giving everybody just a minute to ponder. Then we're gonna vote. I get 51% of the vote.
What was the question again?
Which one of those three atoms is the largest? Who votes chloride? Okay. Who votes argon? You might vote potassium. It's the largest. Okay. Chloride would be the largest. Anybody tell me why?
Is it because, I want to say 'cause it's closer to the, like, I don't know if that'd be right, because it's closer to the nucleus.
What's closer? Closer doesn't sound like largest. All right, Grant, I just want to hear what Grant's got to say. We're coming to you next.
Okay. I think it would be larger because actually.
All right, Hensley, what you got?
It's more of an educated guess than anything, because I know that you can't actually use this reasoning on the AP exam, but I know that the size, like the trend is that it decreases across a period. And because I know that it has to do with, whenever you have electrons, it increases the, what's the term? The effect of
Those aren't on the same period together.
Well, yeah, but it decreased across a period.
Okay.
He said that,
But those aren't, but all three of those don't share the same period. So that doesn't account for potassium's situation.
yeah, I got nothing.
Okay.
I just picked it because of the minus sign. It's just honest.
All right, Grant, you get one more shot.
Okay, I got two different options.
No, we have one chance.
Okay, hold on, let me pick
Says
which one I
you get
want
one
to say.
chance after giving her a second chance.
Well, she went for a third. She
I
wants to
want
get a
another
third.
I was upset.
When do it might be about time for me to have a turn. Go ahead.
So look, so what I'm thinking, I'm gonna go off of what.
Spit it out, Grant.
Okay, first I think maybe chlorine minus because it's the only one that actually gained an electron. The other ones didn't, they lost, either lost or stayed the
But
same.
they all have 18.
Wait,
Well, go ahead, go ahead.
so, hold on, I know I'm lost. Just go. I don't even want to sound crazy.
How many protons does chlorine have?
17.
17. How many does argon have?
18.
How many does potassium have? Who has the highest? Well, since we're asking for the largest, who has the least effective nuclear charge out of those three? Chlorine. Less protons, right? What's holding the electron? Why do electrons stay in an atom anyway?
It's the ZEFF.
They're attracted to the protons, right?
Yeah.
Okay. So if I'm only attracted to 17 protons, then I'm going to be floating around out here, right? But if there's 18 protons and coming in here, if there's 19, it's coming in here, right? So 18, everybody has 18 electrons, right? In that,
My brain is doing the.
I forgot this is everyone pulling on each other.
yeah, because they're being pulled by different numbers of protons. So what you got to find, okay, is what's different about them. That's going to be the reason that they're different. If they have different properties, it's because there's something structurally different. So if you don't learn anything else about chemistry ever, learn this today. If two substances are different in any way, there is a atomic or molecular structural reason for it. Sometimes we can figure that out. Sometimes we can't. Sometimes it's just a little beyond the high school course. Maybe nobody's figured it out. But if two things are different, then the chemical reason for it is structural. There's some kind of atomic or molecular structural difference. So you pick out which one's the largest and you're trying to explain why. It's got to be a structural reason. So if they're different, what's structurally different? Well, we look up there first, what's structurally the same? Number of electrons, right? Okay, so the electron configuration is the same. What's different? Protons. So protons have to be the reason that they have different size or different whatever they've got that's different.
So can you like put the like give me a second to make sense. So you would say that this one is the largest because it has less protons and hence so what? Like can you
Has less protons. If you want to get real good with it, you would say has a less effective nuclear charge,
Could
which
you
is
say,
the fancy chemical way of saying it's got fewer protons.
could you say there's a structural difference of protons because, like you said,
There's no
structural
because. The because is because God gave chlorine 17 and not another number.
difference? Okay, well, say what you just said.
But
So chlorine is.
chlorine has a less effective nuclear charge.
A less, and what's the number way to say it?
It has fewer protons.
Okay.
What'd you say the term was for when they all have the same?
Isoelectronic.
Isoelectronic.
So who's the smallest?
Potassium.
Potassium, because it's got 19 protons.
You know what I did?
What you did?
Okay, so like, you know how I said, you know, that I said that potassium was the highest, you know why I said it? I got it in my paper right here, I promise you. I said K because of the proton number. So I just had it backwards.
But be more specific. What about the proton number?
Oh, that's all I had.
Okay. But what about the proton number, right?
Yeah.
It's higher. So in order of effective nuclear charge, it goes chloride, argon, potassium, right? So therefore it's listed larger to smaller in size. Yep.
So, since it's like, has less protons, does that, since it has 17, does that give it more room to move around than like the 18?
They're just, I hate to use this term, but the electron cloud gets smaller the more protons you add to the nucleus. I'm not a fan of the term electron cloud, but
Well,
because it's vague. It implies that we don't have any idea where any of them are. That's not correct. Yeah, there's a whole bunch of different examples. We can
so, another question. So chlorine has a less effective nuclear charge. Kind of explain what that means. I feel like you have.
There's fewer protons pulling on stuff. So what does it mean to affect something, right? Cause and effect, right? Okay. So what does it mean to affect something? It means to cause it to do something, right? Okay. So the protons are what's holding the whole thing together. If the protons weren't positively charged, the electrons would fly away because they're being pushed by each other, right? So one reason they don't just fly off into the farther reaches of the universe is because the protons holding them, not still, but holding them in that region of space.
On the electrons.
Holding the electrons. That's what the protons do. They hold electrons. So how effective are they at their job? Well, it depends on how many there are, right? If there's just one proton in the nucleus, it's not going to be very effective at holding things. If there's 118 of them, it's going to be pretty effective.
Since there's 17.
Because
or
Coulomb's
19.
law says the magnitude of charge has a lot to do with the attraction and repulsion.
So since it's 17 instead of 19, there's less holding them
No.
together. Okay.
They're trying to fly away. Yes, Grant.
Okay, so basically what we're saying is that whenever so the only time we would really like use this is whenever there's different elements with the same, that's the only time I would even think about it.
No, this is the same explanation as any animal in the same period.
Yes, so any atom on the same period.
Yeah,
this
why
is
are they
what
all
the
different sizes? Yeah.
So any atom on the same.
Okay,
Rate that question.
One more
10.
question. One more question.
Rate that question 1 through 10. The question I just asked, rate it 1 through
0.2.
10.
This is my question. On the test, you're gonna ask us to draw an isoelectronic
All right,
configuration and then say which one is. Is there more than just these three? Are there like
there's all kinds of stuff.
we need to do one?
Could you do it with like the next?
Okay, everybody do this. Everybody do this. Draw another orbital diagram of another atom that's isoelectronic with those three.
Is it like every end? Those three?
Think about it. So draw one more example. There's multiple possible examples, but draw one more. There's two that are very obvious, but there's others. Just pick another different element and draw it isoelectronic to these. Make sure you get the charge correct.
A whole nother set and just pick one new element.
Just one. There's a whole,
So we're gonna have
You could
4
draw.
instead of 3.
you could draw 115 of them.
It can be 2 or 3. So it could be a group that has 2 that's
I
isoelectronic.
could draw all 118 elements isoelectronic if I wanted to, but that's not practical. But there's several that are practical.
One row that one and then have to find 2 more to fix that one.
No, it's a whole new, you erase that whole thing and just find a electron.
I want you to draw an orbital diagram of some type of atom or ion that's isoelectronic with the 3 that are currently on the board. Just pick one. There's 115 possibilities. There's probably 6 or 8 reasonable possibilities. 115 theoretical possibilities. I want you to pick one. Number. So the 2 most obvious choices.
Because on this test, you're pushing.
Do you use it?
Oh, shoot. Wait a minute. It's okay, wait.
Yeah. Okay, I thought I was like, I thought I did it like something wrong too. Was it, because it wasn't hard.
16, bet.
Where at?
Thank you.
Oh, oh, okay, reference. Wait, who are you referring? Is it like the high school or like the middle school? They have Thursday?
Are they being televised or something?
They are. Now watch me on TV.
You gonna be running up and
Who's
down?
not?
Yeah.
Sprinkle in that wall.
What
I
channel?
really want to see that.
We're at
NFHS.
TV 24.
24.
We can watch anything on NFHS.
Yeah.
It's on TV 24.
Are you the, like, that one, like, you would like?
How'd you get to that place? Like, did you have to do like 5 years of reference? But why? I said, but why?
Because I enjoy it. The things that I enjoy, I try to be good at. So.
So how do you feel like, let's say like, it's like, you know, some of the refs right here, like we think about basketball, you got some terrible, like real bad refs. So in football, you know, if you got some terrible refs, like, does that just give you like an ick?
Yeah, because I train most of them.
Oh.
So all of the officials at our home football games last year and again this year are people that I train. So
So if it's a bad
if they
call,
don't,
that
if they
means
don't do well,
it doesn't.
I mean, I take it.
Not
as
actually go back to,
But
because
it's like when kids fail a test.
you taught them the right stuff, it's
Yeah.
just how they interpret it.
Why are we
Like
not
this
doing
next
what-
quiz, you know?
Yeah, like why are we not doing what we talked about, you know?
Yeah.
So are you not allowed to officiate Jacksonville games?
Not on the field, I can work with clock stuff like
Okay.
that, but I can't do
Yeah, cause I remember, yeah, cause you did the softball thing, didn't you? You were at softball that 1 year, remember, we had like a softball game, it was the teachers versus students.
Yeah.
Yeah,
He
you
was a
were at that.
coach.
Oh, so.
I used to umpire softball.
Oh, so you just dibble and dabble. in it, like,
Actually,
all
he used to
the-
be a-
I dibble and
he used to be a
dabble in
softball coach.
basketball.
He coached the high school.
I dibble and dabble in basketball. and
She didn't know you were a
softball.
softball
I didn't know you was a
coach.
I don't
softball
dibble
coach.
and dabble
I didn't know
in
that
football. I'm-
He used to be a coach.
I didn't know you used to be a softball coach.
Yeah.
Hell, I wouldn't.
Well,
Yeah, like I said.
you coached me one year.
I did. I mean, I did.
But yeah.
Okay.
It's one of those deals where my kid was playing and they didn't have a coach to have a big team, and either I coached or they didn't have a team. Somebody had to do it, so I did it.
Oh, would you be a, would
As
you be
soon as
like
they
a
had
coach?
somebody else to do it, I got out.
Would you be a coach of like football, like just helping out? Like, as an
I thought about it,
overall?
my problem with coaching football
Cause them boys, I know they had attitudes.
is that I get very, 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 very serious about the sport of football. So I don't know if it's healthy for me to be a coach.
So you, okay, so you'll probably be one like yelling at kids, like, what are you doing?
No, I would be, yeah, probably. I would be really hard on myself. Too. I don't know. Because I'm pretty bad about my fishing. Bad enough.
Are you gonna be a Nick Saban? Like, if you like Nick Saban, like he's
He's
still
not
his head.
official, he's the coach.
Well, I'm talking about like if you were a coach,
I'm
or
not.
let's say the, like,
Nick
if you stole the head.
Nick Saban is actually relatively very calm. So.
Okay.
So, it'll still.
Well, the players know, to officials he doesn't bother officials.
Oh,
He
he
bothers
broke
coach.
his.
He's his own.
You did two cents, Mr. Cato. Are you positive that if we were to get a ghost flag, you would coach us?
I'm 100% positive that I'm
Why
not.
not?
Can you handle the truth?
Yes.
Yeah.
Okay.
Girls are.
Girls can't handle contact sports.
I agree to
Just
disagree
saying.
on
Yes,
that.
I'm
I don't, because I've officiated girls basketball too many nights.
You talking about?
I am. Y'all can't deal with contact. You can't deal with
It all depends on what type of
Take
contact.
Take it personal.
Just
Exactly,
like-
that's all.
Just like,
Always
and like if
You
you
just
come
proved
in.
my whole point.
Look on the video,
Proved my whole point.
If you come down wearing a good one right here, you just push me out the way, like, what I'm gonna do right there? I'm not
You're
gonna
not
fight you
supposed to do
with you.
anything, because basketball is a contact sport, you're not supposed to do anything about it. The official calls a foul, and you go shoot your free throws, and that's it. But girls can't do that, y'all can't handle it.
Oh, yeah, yeah.
Been there, done it,
Right.
got all the t-shirts, been there, done it.
Now.
Done it. Football's a collision sport, flag football is a contact
I
sport,
know, I'm saying like.
just like basketball.
They
And
could,
I've
they should
had
make it a collision
so
sport.
many nights.
real.
That would be
Oh.
so cool. Have
So
someone take
many
your ear
nights of
out.
basketball experience. Where I can call a girls' game at 5 o'clock and a boys' game at 6:30, and the same plays happen in both games. And in one game,
Oh, this
everybody gets mad, and the other game, nobody says a word. Because,
Mr. Cato, Kalani May is checking
All right.
out.
so, and I've got stacks and stacks and stacks of evidence
Okay,
that
so.
y'all can't handle content.
Okay, I have another.
Emotionally, you can't deal with
See you
it.
tomorrow.
Take
So
it
like,
personal.
are you the type that never play basketball, never play basketball, you're fishing, they get in a fight? Are you guys going crazy?
No, we're not allowed.
I'm not the black
Heck,
ears.
heck,
Just
heck.
unicorn.
Oh, so these people break it up?
Coaches.
Oh.
We're not allowed to break up fights. So
Oh,
what you see on TV with college, so I call college football too. I have not this year, but I have. We break up fights in college football, but you don't do it in high school because the players are in the team. So if a fight breaks out in the football game tonight, like, fight breaks out tonight, blow a whistle, I'm gonna throw this flag for that one fighting and this flag for that one fighting, and then I'm gonna stand there and start, I'm gonna take out my pen and paper. And I'm gonna start writing down the numbers. And when the coaches get them through, get them off each other, we're gonna tell each coach how many people we just disqualified, and if they got enough left to play, we'll go back and play. If they don't, but I don't get in, we don't get in the middle of it.
Has that ever
I'll be
happened?
late again.
Has that ever happened where they've had to forfeit because they all got in a fight?
I had a game one night where it's probably what we should have
Full team
done,
fight, could you imagine?
but it was 10 games, so we had to figure out the main participants.
Everybody
Duke it
fight
down.
Taylor, can you do 2 examples? You do one with calcium and potassium and then.
Well, this is, hang on, here's the two most obvious answers to the question. Okay.
Oh, yeah, we did.
Yeah.
All right, so these are the most obvious answers to the question. Okay. There are technically, theoretically, 115 answers to the question. Okay, like for example.
Oh, wait, what's the Justin bid one?
For example, if I said draw, just think about this a minute. If I said draw the orbital diagram for uranium 74 plus,
We'll see.
what would that be?
It'll probably happen.
Did you just say, oh my gosh?
Yeah, what if I said, I mean, this is theoretical, I'm saying there's 115 theoretical answers to the question. Number 92,
Oh, I see it, 92. Oh, you do 92 minus 74. You get that in.
18 electrons,
You are
right?
guardian?
So if you drew that, okay.
That is crazy. We never argue.
Now, that's what I meant by theoretically possible, but not practical, right? That's not gonna happen. The energy required to take away the 74 electrons of uranium would be at the temperature of the sun, okay? It's gonna be extremely high, it's not gonna happen. But theoretically, it can happen. So there's theoretically, I could pick any of the other 115 elements on the table and draw a configuration that's isoelectronic for these three, okay? The only practical ones are the metals on the fourth row and the non-metals on the third row. Okay, so third row non-metals, stable anions, and fourth row metals, stable cations are the potential reasonable answers to the question. So we did calcium, we could go through some of the transition metals, the D block, if we take all the D electrons away. We get over to what's underneath the aluminum.
So we could still say.
Gallium, so on and so forth. Gallium 3 plus, and so whatever. Anyway,
Can you answer the question, which one has the largest atoms, even if it's not a 10?
yeah, so this is larger, this is smaller.
The calcium would be.
I'm sorry, I said it backwards. Smaller, what'd I say?
You said
Say it
calcium
backwards.
was larger.
Smaller, larger. This one would be really small. It's got
That would
92
be smaller?
That would be really small. It's got 92 protons pulling on 18 electrons.
Okay, yeah.
Draw it up like this.
No, you didn't know.
Well, I mean, I noticed they weren't there. but-
Hold on, let me make sure.
Like, the first time I saw it, like, I thought.
We're like, uranium 198.
Two or more.
What?
Because they put it like, uranium 198.
I feel like y'all jinxed my game tonight. We're gonna have a fight now.
But there's like, it's.
Mr. President,
No, there's not.